Good morning. Welcome to Discover Engineering. I'm Beth Stevens, Manager of Education Relations at Hewlett-Packard Company. Hewlett-Packard, an international company, manufactures measurement and computation products that are sold in approximately 100 countries. Our products are used in industry, business, science, engineering, medicine, and education. We're very pleased to sponsor this broadcast during National Engineers Week. This sponsorship is done jointly with the County Office of Education and the Industry Education Council. We're very happy to be a part of Discover Engineering to give you the opportunity to look at real-world applications of the science and math that you're studying every day. Throughout the week, approximately 20,000 engineers are visiting in classrooms with students just like you. In fact, perhaps an engineer is there with you today. This is an opportunity to explore the world of engineering and to discover real-world applications very similar to the ones that we might use in our company. Hewlett-Packard is affectionately referred to as HP here in the Valley. We have about 20,000 employees, and schools and students like you are very important to us and to our future. So enjoy the program, develop your talents, and follow your dreams. Thank you very much.
Good afternoon. Welcome to Discover Engineering, or if you're watching from the West Coast, good morning. Hello, my name is Harry West, and I'm a professor at MIT. I teach engineering design. I'm going to be your host this afternoon. We have some very important people here in the studio, and this show is coming out to you live, I would like to remind you. Let me introduce you to a few people in the studio. Most important of all, we have students here from the high schools of Boston and Cambridge, and we have engineering university students from MIT and from Northeastern. Thank you for showing up. We have teachers from Boston and Cambridge. And we have the headmasters of schools from Boston and Cambridge. And shortly, we'll even have a mayor of Cambridge. The mayor of Cambridge will be joining us in a few minutes. And with us also we have Eleanor Baum, Dean of Engineering at Cooper Union, and David Mealy, who's in engineering at IBM. Thanks for joining us here. What is the purpose of this show today? What we want to try to communicate today is what engineers do. What is the engineering process? And there's a few basic lessons we want to be able to get across. One is that engineers design. We create new products. I know one product that all of you have in eyesight right now. That's television. That product exists because an engineer designed it. An engineer designed it and figured out how to manufacture it and sell it and getting out to different consumers like you. How did that engineer do it? How did those engineers create that television? Well, it was a process. It was an engineering design process. We want to teach that process to you today. And as a vital part of that process, of course, is science. That's what you learn at high school and at university. Math and science is a vital part of that engineering design process. It's not all of it, but it's part of it. Now, if you have any questions or would like to phone in, please do so. We'll be answering questions in about 20 minutes, but please prepare your questions. The telephone numbers are 617-253-6753, or if you prefer to fax, you can fax to 617-253-8301. So first lesson we want to get across today is that engineering design is a process and science is part of that process. The second lesson we want to get across is that those design engineers, those people who created that television in front of you, or all the other products that you use, they didn't get to be engineers by magic. They also followed a process, an educational process, started in school, went through to university in their companies, and they're always learning. They're always getting better. Okay, so these are the main lessons we want to get across. The design process, the role of science in that process, and of course, the importance of the educational process in acquiring these skills. The show is going to be very busy. We're going to have to work very hard to get through everything that we planned for you this afternoon. And before we move on, I would like to just express a very personal note of thanks to the people who've made this show possible. To National Technological University out in Colorado, to MIT, this has been partly funded by MIT, but most especially to Hewlett-Packard and Motorola, because their funding has made this show possible. Thank you very much for doing this. Okay, I think I've said enough now. Let's get some comments here from Dean Eleanor Baum. Eleanor Baum has a PhD in electrical engineering and is chairman of the Engineering Dean's Council. She's going to hate me for saying that. She's chairperson of the Engineering Dean's Council. Eleanor.
Hello, and I'm visiting today from Cooper Union in New York City. Got to put in a plug for my school, Harry. Can't leave that out. Every time we pick up a newspaper, we read about serious problems in our society. We read about the crumbling infrastructure. We read about the need for more housing. We read about ourselves falling behind in manufacturing. We read about the need for new food. We read about new developments in healthcare and the interaction of medicine with other kinds of processes. It is very easy to read about all of these things and say, yeah, that's tough, but someone's got to solve those problems. And that's the kind of thing that engineers do. Engineers are trained problem solvers, and the kinds of problems that they decide to solve are problems to make society better, to make life better for people, to improve the human condition. So engineers do very, very important work in this world. How do you know when you're a high school student and you're taking lots of courses and you're being exposed to lots of different things, whether you ought to be thinking perhaps about a career in engineering? How do you know that engineering is for you? Well, as Harry had pointed out, certainly engineers are people who are comfortable with math and with science. Now that doesn't mean you have to have aced every math course you've ever taken, but it does mean that you have to be comfortable with mathematics, because mathematics is really the language of engineering. If you're such a person, if you're someone with a curious mind, if you're someone who's looking for a career where your whole life you're going to be learning and growing and doing different kinds of things because technology changes enormously, then you may very well want to be an engineer. And hopefully a show like today will give you a greater feeling, not only about the kinds of people engineers are, but what engineering students do and what they're interested in. So I'm looking forward to this being very informative and fun.
Thank you, Eleanor. I think that's a very profound point that you raised there. You know, we have a lot of problems in our society. We have problems, say, let's take a typical problem, the greenhouse effect, problem of thermal warming. You know, doctors can help people or help animals and plants that are suffering as a result of these problems. Lawyers can sue people. Managers can assign costs, but the only people who can really solve these problems are the engineers. We're the problem solvers. People criticize engineering sometimes because some of the problems have been caused by engineered products in the past. That's true, but the only way we can solve these problems in the future is by engineering. There's no way that a politician or a lawyer or a doctor can solve these problems. It's up to us. I'd now like to introduce to you an experienced engineer, David Mealy, who's an engineer at IBM. He has a bachelor's degree in industrial engineering and a master's degree in management of technology, which he actually got through the National Technological University, through this very same satellite link that you're watching us on right now. David.
Thank you, Harry. Hello, I'm a manufacturing engineer with IBM in Poughkeepsie, New York. Our mission is to develop the automated tooling used to manufacture IBM's largest mainframe computers. We design and develop the equipment as well as the processes used to manufacture this. I brought with me today a substrate, a TCM, which is used in the mainframe. About 10 or 12 of these make up a mainframe computer. We have an array structure here where we join logic devices using automated robotic machinery. We use sophisticated lasers and wiring equipment to edit the circuitry on top of this substrate. So you can see that there's a very complex environment which we attempt to engineer these tools. At IBM, we're very focused on our customers' needs, and our customers' needs drive tremendous engineering challenges. These engineering challenges, to meet these engineering challenges, IBM has many engineers, and they have a variety of careers and interests. They have some specific skills, like optical engineering or ceramicist or software engineering, but they also have some common skills. And today, maybe we'll talk some more about what those common skills are, but clearly their creativity, the ability to use or take a look at a problem in a different way and use maybe a common solution in an uncommon way to get a more creative answer. But probably most important is teamwork, the ability for the engineers to work together in team in a constructive environment. Jack Keeler is president of IBM. He's also an engineer. He's also chairman of this year's National Engineers Week, and he's put together a tape which begins to look at the variety of careers within engineering. Let's watch.
Hello, everybody. I'm Maxine Yee. Once again, engineers across the U.S. will have the opportunity to help this country meet its need for engineering skills. To help, engineers can participate in a nationwide school outreach program during National Engineers Week, February 16th through the 22nd in 1992. One engineer who's participating is IBM President Jack Keeler. Jack is the 1992 honorary chairman of National Engineers Week, and he's doing all he can to encourage a big response from engineers. Jack, why is National Engineers Week so important?
This is the 42nd year we've done this, and we use this week to generate public awareness of the engineering profession, Maxine, to help people understand what engineers do as well as recognize some key engineers. We ask 50 engineering societies to participate, and we generate teach-ins where we ask engineers, in fact hopefully 20,000 in number this year, to go to schools and meet with counselors, teachers, and students and help them understand what the engineering profession is, why it's important, and excite students to want to go into it.
Engineering is important, especially in gas plants such as this one. Our resources are getting more and more scarce, and we want to ensure that we do as much as we possibly can with all our resources. Here at the turbine, my biggest job is what they call a monitoring engineer or a quality control engineer. And I see here that the demethanizing pressure is about 300. And then the chromatic gas methane to ethane ratio. Yeah. To us, quality means having as little waste as possible and working as efficiently as possible.
Imagine taking a slice out of your torso and pulling it out, and you can actually look down on the stomach or the heart, depending on where you take the slice. So it gives you a different view. It gives you more accurate information.
We're very focused on making sure that we can make the best images for doctors to use in creating scans of patients in order to diagnose disease. You can take the picture of the person that we get in from the scan, turn it around, look at it from different angles, reconstruct it into something that's a useful picture for the physician. The nice thing about medical engineering is you know that whatever you do, no matter how small or how big the task is, that is really going towards something that will be used to save another person's life. And for me, that adds a lot of meaning to my work.
And specifically what I am is an application engineer. I apply technologies more than the scientists that stay in the back rooms with the chalkboards and they write all their formulas. After they're through with the formulas, they come up with a technology. I'm an engineer who takes that technology and then applies it to the real world. This is a technology that we took in from NASA, $10,000 glove, has a sensor, has optic fibers, knows where your hand is in three-dimensional space. We try to apply it to the toy industry. Our first product was a thing called the band of the hand. Piano, keys, chords. We have a drum, snare. Here, this prototype demonstrates the technology. The glove knows where your fingers are, and the prototype here shows you that we know where the fingers are. This is the final product, the Power Glove, the one you can buy in your local store. We use ultrasonics here to determine where the hand is in three-dimensional space, and we use geometry to figure that out. We have another technology in the fingers to figure out what your fingers are actually doing. How this works with Nintendo, we'll show you. It's Super Glove Ball. The hand on the screen moves in real time with my own. I can catch the ball, wipe out the cubes. I can make my hand like a gun, fire bullets out of my fingertips. Basically is being a little kid for a while and then taking our tools that we learned in school and applying those to the things we like to do best, and that's make toys.
The microphone output.
It's plus or minus 15 volts is the voltage it runs on.
Look at this. Look at your power supply output. You're getting nothing coming out.
This is the schematic diagram.
This is one of the senior projects we're working on. Testing. Digital voice recording.
What engineering, I believe, really did for me was teach me how to think.
Testing.
It works. Yes, it does.
Hello, welcome back to the studio. You know, this show is going out live all over the country. Let me just read out a few names. There's a site, an AT&T site in Little Rock, Arkansas. 3M is participating in St. Paul, Minnesota, and a Micron Technology in Boise, Idaho. Thanks for joining us. We have a very full schedule for you this afternoon. There's going to be some design contests, some tapes. There's actually going to be a live contest between the high school students from the city of Boston and the city of Cambridge. There's also going to be a real live engineering research project ongoing in the background in the studio throughout this afternoon. Let me introduce you to this project. What we have here is an engineering research project. Normally, these students are working on this project down in the basement of this building. But to show us what they're doing, they've brought their robot and their computer and their sensors up here to the studio, and they're just going to continue working on this problem over the next couple of hours. Let me introduce you to Nate Delson, who's a PhD student working on programming this robot. Nate, tell us about your project.
Hi. This is a robot, and my research goal is to develop an easier way to program robots. Robots are very useful because once we get them to do something that we want them to do, they can do it over and over again. They don't get tired. They don't complain. They're the perfect type of person or helper you'd want to have around. The problem with robots often is that they're very difficult to program. So my goal for this research is to be able to program a robot to do a task as easily as I could show one of you how to do that task. James now is going to demonstrate how this program works by showing a typical task that we might encounter in the house, such as taking a cup out of a dish rack.
let me introduce to you James Pinkney, who's a master's degree student here at MIT, and he's actually developed this end effector that he's using down there. And in fact, we're using here the same technology that we just saw in that video that was prepared by IBM. James, tell us a little bit about what's going on here.
Hi, I'm James Pinkney. My task is to develop hardware with which we can train or teach the robot. Now, the criterion that I had in mind when coming up for these tongs was that they be lightweight, easy to use, intuitive to use, in fact, and that they don't subject the hand to a lot of wear and tear. Now, these tongs, if you can see them, have 4 sensing resistors on either side, which give tactile sensing, or allows one to tell the computer to tell when the tongs are closed. Also, there is a position sensor, which gives the position in space as we move the part around. And if you look at the human hand, it's quite a good end effector. It's a very clever design. This one was very simple. And
I just want to say a few other things. This research project is actually very exciting because robots, people have talked about robots a lot and we've seen them in the movies, but really if somebody wants to program a robot, they need to take special courses and learn a special language. And if we want to sell robots and have people willing to buy them and use them in their house, we'd have to have something that's as easy to program as what James just did. Right now we're going to have the robot duplicate what James did with the cup. Hopefully the robot will take it out of here, but this is an ongoing research project, so we never are sure if it's going to work or not. So let's see. It's moving slowly, but it seems to be on track. This is duplicating the motions that James just did a few seconds ago. Success. We managed to take the cup right out of the rack. All we, I guess, need to do is to teach it a bunch of other things.
Thank you, Nate. That was a great demo. You know, all this morning we've been practicing, and it never worked once practicing this morning, but it worked here first time. That's great. This is an engineering research project, and those 2 students, James and Nate, are trying to develop a new product. They're trying to design something new. What is the process that they're going through in trying to design something new? It's not magic. They didn't get to that demonstration immediately. It didn't work. It hasn't worked for a long time, actually, but it's now working. What is the process they got through in doing that? Now, I think that most of you already have this handout. We mailed it out to you a couple of weeks ago. And I'm going to teach you a little bit about the engineering design process. The first point is we have to understand the problem. We have to identify a need and understand the problem. The need that Nathan Delson and James Pinkney have identified is they need an easier way to program robots. There's a need for that because then more people could use them. That's a real need. And the problem is that right now, if you want to program a robot, you have to do it with a keyboard. And they are trying to develop a new technology so you don't have to use a keyboard to program that robot. They came up with a whole bunch of different concepts. Different types of sensors, different types of interfaces, different types of mice that would have enabled them to continue with their project. And they selected one. They selected one particular concept, which is the one they showed you, that very simple tongs. They decided how to make it. James made this device. He designed it. He built it. He actually optimized the design of that. He got the shape right, the strength right. He applied some physics. He applied physics. A lot of physics here. He made it, we tested it, and it worked. Normally it doesn't work. Normally, at any one of these stages, we often stumble across problems. We find that we've created a whole bunch of concepts, and when we come time to select them, none of them are satisfactory. So we have to go back in this loop and try to create new concepts. Often when we get down here at the testing stage, we find that it doesn't work. We have to go all the way back here and say, did we really understand the problem? The design process is highly iterative. It's highly iterative, it is a process, and it includes science. Now over here, I prepared some slides that I'm going to try to show you to fill out a few more details on this design process. And we have a very clever setup here. Down here, I have a Macintosh Quadra 700 computer, a state-of-the-art workstation. And this has got at its heart a Motorola 68040 chip. That's what makes it so fast. Now, if I can remember the key commands here, we can get to some slideshow. What I'm going to do here, I press Control 1. Here we go. And I can now change to a different program. Change to the PowerPoint program. And we're back to that slide that I originally showed you. Now I can actually run through a slideshow using this graphical interface here. Here we go, onto the slideshow. Here we go. This was the slide we originally discussed. This is the engineering design process. Part of my job at MIT is to teach students how to design. A lot of times people try to go straight from the problem, understanding the problem, to the final answer. We can't do that. It's too difficult. By pressing a button on this mouse here, I can go through to the next slide. I love this technology. It's great. Yay, it works. There are lots of models of the engineering design process, and this is one of my favorite here, developed by New Jersey Technology Education. Vince Walensik down in Montclair State College, I think, is one of the principal people behind developing this model. There are various, you can develop different design process models in various levels of detail. Some couple of guys in Germany wrote a 300-page book on this subject. But basically, they're all trying to describe the same thing. We go from a need through analysis and investigation to try and understand the problem properly, generating solutions, choosing a solution, developing a prototype, testing, redesign, and asking ourselves, what did we really understand that need? Now I'm going to go through a little bit of a design problem here. And we're going to look at brainstorming and idea selection, or concept selection, live in the studio. The rules of brainstorming are, any idea is a good idea. Just throw ideas out. Write down the ideas as they come to you. Don't criticize other people's ideas. And there's no ownership of ideas. If somebody else suggests an idea, you can take that idea yourself. We're going to look at a very simple problem because we don't have much time here. We want to get through this quite quickly. The problem is, and Eleanor Baum is the presenter of this problem, Eleanor has just has just come up from New York to Boston, and Eleanor has to get back to New York tonight. What are the various ways of getting from Boston to New York? Well, let's understand the problem first. How far is it from Boston to New York? I'm just going to solicit people in the audience here. Susie, how far is it from Boston to New York? Ballpark. 250 miles. I agree. And it's a long way. We're not going to walk that far. So we understand some basic parameters here. Now let's brainstorm the various different ways we can get from Boston to New York. Let's take some suggestions from the audience here. Millery. Train. Okay, train is a good idea. Okay, any other ideas? This is not so difficult, you know. I think pardon? A car, okay. A car, and I'm writing down these ideas as they come to me. Okay, another way to get from Boston to New York. Plane. A boat, okay. You couldn't do that if you're trying to get from Denver, Colorado, but you can from Boston. A bus. And hitchhike. Okay, I think we have a bunch of ideas here. So we went through a very simple brainstorming process. Now, let's try to select between these different concepts. And now we have to go back to the customer, to the person we're trying to provide a service for. We have to go back to Eleanor Baum. Eleanor, what are your important criteria? What's your main criteria for selecting which way you're going to get from Boston to New York?
Time becomes a very important criterion. I've got a very important meeting that I've got to get to.
Time. Time is the main criterion. Are there any other criteria that we should include?
Sure, I want to get there safely.
Safety. Okay. And anything else?
Yeah, how much it costs, I think, would matter, don't you?
Dollars. The bucks. Okay. Now let's do some analysis here, some very basic analysis. let's try to estimate how much time it's going to how much time it's going to take to get from Boston to New York by plane. Any idea by plane? An hour. Okay, 1 hour. By train. Well, we've had various estimates here. But let's say 5 hours. Hitchhiking. Forever. Infinity. It depends. For me, it would take forever. Car. We can apply some science here because we know the distance. It's about 250 miles from here to New York. How fast does a car go? 50 miles an hour? We stick to the speed limit. So we're talking about maybe 5 hours by car. Okay. Now, which is the most important criteria for you?
The most important criterion really is the time.
Okay, time is most. But let's look at safety. Which is the safest way to New York? Let's try to just arbitrarily.
Hitchhiking is not.
Hitchhike is not. So let's say plane is fairly safe.
Plane is very safe.
Okay, very safe. Safe. Train, safe.
Safe.
Hitchhiking, unsafe. Car.
I'm a terrific driver.
Suppose I was driving you to New York.
Well, then we'd worry, Harry.
Okay. For most people, a car is a fairly dangerous way to travel. You know, about 40,000 people die every year because of car accidents in this country alone. Let's say it's neither safe nor unsafe, okay? Dollars. How much is it going to cost to fly? Maybe $150?
Probably.
Okay. By train? $100. Okay. Hitchhiking? 0. Zip. And by car? $20? Okay.
Something like that.
An estimate of $20. Now we've compared all of these different concepts, but they're all in different units. Let's rank them. If they're good, let's call it 3. If they're medium, let's call it 2. If they're bad, let's call it 1. Okay, so a plane, in terms of time, is ranked very highly, and I'm going to switch to a different color here. Okay, a train is medium, say. And a car is medium, and hitchhiking is very bad. I'm going to give it 0. Safety, plane is good, train is good. Hitchhiking is bad. Car is medium, I'll give it 1. Dollars, plane is not so good in terms of cost. I'm going to give that 0. Train is medium. Hitchhiking is very good. And a car is medium again. Let's add up these and see what we get. We get here 5, 3, 6, and 6. So according to this, we can't really decide between a plane or a train. But Eleanor told me that time was of the essence. The most important criterion was time. So I'm going to say that since this basic analysis suggests that planes and trains are equally good, but the plane is significantly faster, we should suggest to Eleanor that you go back from Boston to New York by plane. And I admit we didn't have quite enough time here to go through this properly. You see, we're on a very tight schedule here. We're doing a tricky project management problem. We've got to get the product out, the means of transportation for Eleanor. We've got to get it out within the next 30 seconds or so because we have to move on to another part of the show. And we've got to meet the spec.
But
Eleanor,
Harry, we have a problem.
I think you should go by plane. What's the problem?
Suppose it turned out I was afraid to fly.
Oh, no. We forgot to ask Eleanor the basic question. Do you like flying? We forgot to properly understand the voice of the customer. We forgot to do a proper marketing study. Often that's a problem in engineering.
Yes, it's a very, very serious problem because you can come up with an absolutely terrific device or product, but if for some reason your customer doesn't want it, what's the point? So that too becomes a very important part of the design process. The customer's wishes, the customer's input.
A lot of people don't realize that engineers have to spend a lot of time working with customers. We don't do just math and science. We have to do everything. Let's take a look at this next slide. And this gives one of my pictures my impressions of what the design process is all about. We use science. Science is a very important part of our skill, but we have to know more than that. We have to know about the engineering elements that we're using. In my case, because I'm a mechanical engineer, I'm very concerned with machine elements. We also have to have some intuition. You know, a lot of the decisions we make are not based just on science. We also have to be very creative people. We have to come up with new ideas. And most important of all, we have to be good at communicating, because engineers work together in teams. As David Mealy was talking about, engineers are team players, and if you're working in a team, communication skills are very important. Now, I could go on and continue with this analysis of the engineering design process, but rather than do that, let's take a look at how some MIT students learn to understand the engineering design process in a sophomore level class here in Cambridge, Massachusetts. Let's take a look at the students doing their Introduction to Design class.
In the battle for the balls, which strategy is on target? Come join the excitement on Scientific American Frontier.
GTE brings you more than the power of telecommunications, light, and precision materials. A grant from GTE also brings you the power of a new world in Scientific American Frontiers. At GTE, the power is on.
This is the hottest ticket at MIT, a contest that packs the largest hall on campus. For the spectators, it's a battle of ingenious machines. But for MIT's engineering design students, it's the grand finale to a semester of hard work. And this year, there's more at stake than grades and glory. The best designers will go on to Japan for an international tournament. This is the challenge. Build a machine that can capture tennis balls from the pyramid atop this mesa. At the start, the machine must fit within a 1-foot cube on the starting square. What makes the task more daunting is that it's a race. Another machine starts here, and both students have 30 seconds to get as many balls as possible into their troughs on the far side of the table. If you end up with more balls in your trough, you win. The red ball, it's there to break ties. 6 weeks before the big night, every student receives an identical kit of materials and motors. Then it's into the shop to tackle the toughest part of the course, transforming the box of parts into a machine that actually works. We're going to meet 4 of these eager engineers in training: Aaron, Susie, Charlie, and Anton. And find out some of what they've learned. But now, on with the contest.
Are you ready? Yeah.
Aaron's up early, and right away, he runs into trouble. The metal loop is supposed to lasso the balls. It misfires and flips his machine onto its back.
Oh, I misfired again, dude.
A quick recovery, and he's upright again. But now he's got to drive up to the tennis balls and knock as many as he can down to his side of the table. His machine's not working the way he designed it. But all that matters is getting balls into the trough.
I was gonna catch the stack and then pull so they would land in here. And I built this fine container with this fine door, and it didn't work. I flipped upside down, but I turned myself over. I got lucky, I got really lucky, but it was fun. God, it was so much fun.
The last seconds before a match are nerve-wracking. After all, it's a final exam on stage in front of 500 people. Susie started planning for this moment weeks ago, when she got together with some classmates to brainstorm ideas.
I mean, if you could get 2 machines that could detach and attack 2 different areas at the same time, it would be ideal. Yeah.
Susie's vision of 2 machines may be brilliant or foolhardy when there's only 6 weeks to turn design dreams into reality. And building complex machines takes more than screwdrivers and hammers. But through it all, Susie hangs on to her scheme for 2 machines. She's built a bulldozer to tackle the offense. Now she's struggling with a spring-released wall that she'll use for defense.
It's going to go into the trough of the other person, and hopefully these rubber bands will trigger it out.
The trigger is sticky, but it works. In the contest, Susie's bulldozer gets off to a fast start. Then it rocks back and forth to deploy her wall in front of her opponent's trough. Now she can race the bulldozer around to collect tennis balls and anything else that gets in her way. Just 1 ball reaches her trough, but that's all it takes.
Trigger worked. I'm happy. I'll do better next time. I'm psyched and made to the second round.
To pull down that imposing stack, a net seems like an effective strategy. And there are many varieties of nets in competition. But nets have a problem. They can get tangled. Charlie recognized that flaw in the shop and came up with a more streamlined approach.
As soon as the power is turned on, I'll pull the switch and it'll fire this thing out. And this will open up like this and go over the pile of balls. Then I'll just drag the whole thing with my car. And I was testing this and I found that I don't even need a net. This will just do it by itself. So, you know, a net would just get up, tangled up in the balls. So I was pretty psyched about that. Cut down my work by a lot.
In this match against a net, we can see why Charlie's design is better. His heavy projectile pulls down the pyramid more effectively than a net. But right here is his most important innovation. He releases a string and leaves the projectile behind. That means it won't get in his way, and it makes his vehicle lighter and faster. While the net machine pushes around its useless front end, Charlie's more maneuverable tractor is pushing balls into the trough and demonstrating its contempt for nets. Anton has also designed a wall for defense. He built it quickly, then ran into some surprises in the testing room when he dared a classmate to try to overcome his wall.
Good job. Gee, small problem. Center of gravity doesn't look like it's inside the trough there, does it?
Anton starts to gloat.
Keep on pushing. I don't see balls going.
But then...
Whoa, whoa, whoa. Wait till I make it a bit.
Oh, you have to redesign it, Anton.
No, actually, it's just...
You have to redesign it. Oh my God.
Exposing design flaws is the reason testing's so important. And Anton hasn't finished learning yet.
My screws are a bit too long on the side, which means that you can push these balls over the edge and into the top of the wall.
I like that.
Another problem is you can push it out of the way. So that's what you do.
In fact, for most machines, testing means struggle and failure.
That didn't work. You have a traction problem, not enough weight.
But on the positive side, when the machines are this far along, students can get helpful suggestions from the instructors.
All you have to do is widen that about 2 inches, and then you can win. Okay, it's going to work.
And the pace accelerates. Redesign, rebuild, test again, and try to keep learning from all your mistakes.
Well, I've improved the wall with 2 sort of basic things. I increased the weight of the wall by just putting this heavy metal piece on the back. It just weighs 5 pounds, so it's very hard to push. And I've also put square wheels on it, so in essence, if you're trying to push it, you're pushing square wheels, turning square wheels, which is really hard to do. And I've also flattened the sides off a bit, so you can't just bounce the balls off the side onto the top. And hopefully it'll work really well.
In the contest, Anton's extended the wall, but he triggered it too early, and it's not in the trough. That forces him to fight a battle in the trenches, and he pulls off a narrow victory.
We did it, so I'm happy.
Yeah.
Some matches are classic duels. But in other matches, the machines aren't quite on target. And just climbing the hill is too much for this pair. These tennis balls are frustrating a lot of students. One rogue entry sums up their feelings eloquently. As the contest moves into the next round, some other designs are emerging as strong contenders. This wall unfolds smoothly, and the speedy tractor wedges it solidly in the trench. With perfect placement, it takes just one ball to win. But pinning the opponent's vehicle is a more impressive victory flourish. Here's another strong starter. As this machine pulls down balls, it gobbles them up. Then it trundles toward the ditch. And this feeding machine doesn't even have to unload. It just parks right in the trough. A slick design that could win it all. Watch the machine on the right. It pulls down the balls with a belt. Then the tractor's front end flicks the balls into the ditch. This belt machine is another strong threat. Meanwhile, Aaron's machine is forging ahead, even though it's never worked the way he designed it.
The secret of my success is that it's slow and it's powerful, so I can drive it well. I dismantle the arm because the arm doesn't work, and so I'm beating people that their machines mess up because I can't screw this up now. It's literally a tank now. That's all it is now.
Now that he's abandoned the erratic metal ring, his tank just racks up balls to clinch the victory. In round after round, the pattern is the same. Aaron nudges home another winner and keeps on advancing.
Are you ready? Go!
Anton's up again. He heads directly for the other player's trough and unfolds his wall in just the right spot. Now he drives over to knock down some balls. And then bad luck strikes. The red ball rolls right into the opponent's corner. That really rattles Anton, and he loses control. Fierce competition is taking its toll.
I was just too nervous. I just drove off the table. I just couldn't handle the pressure, you know.
Nerves, I think.
Nerves, yeah.
Just forgot how to drive.
Charlie is winning one match after another. His V-shaped projectile consistently pulls down most of the stack. And that's not his only weapon. He's also got the speed to clean up balls all over the table. We're into the late rounds now. All the machines still running are strong, and every match from here on figures to be a fight to the finish. Case in point, this wall is perfectly placed yet again, and its designer is already starting to celebrate. But even when you do everything right, things can go wrong. The stubborn wedge machine drives two balls under the wall. Last-minute victory is a thrill for the winner, and a stunning disappointment for the loser. Aaron's up against a cute and tricky penguin machine. This time, the tank is too slow and steady. The penguin beats him to the top and snags some balls, including the red one. Then Aaron bumps a few balls to his side. After a heart-stopping roll, only two wind up in his trough. That makes it 2-all, but the tie-breaking red ball is on the other side, and Aaron is knocked out of the contest. Susie's turn now against a projectile machine. The smiley face design is camouflage. This projectile is taking very serious aim. Meanwhile, Susie's gotten herself stuck in the ditch. And when she works her way out, she jams her wall right up around the red ball, on her opponent's side.
My driving drove me to the ditch. I really wish I hadn't because I really think I could have won that round. But I got lucky last round. Those are the breaks. So let the best man win.
The best man will be Chris, Pat, Pete, or Charlie, the only one of our original group still in the running. These four have made it this far because they designed take-charge machines that can attack the stack, collect balls on the table, and deliver them to the trough. In the first semifinal match, Charlie, with his detachable projectile, faces Chris and the belt machine.
Plow, 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 plow.
One emphatic push, and Charlie's headed for the finals. The other semifinal pits Pete and his feeding machine against Pat and the Penguin. Right from the start, the Penguin is hopelessly outclassed. Pete's feeding machine swallows up a cartload of balls and then plows into the trough. That sets up the final match of the contest. Six weeks of frantic work, of designing and building and testing has come down to this moment.
Ready, go!
The projectiles collide, and just 3 balls roll Charlie's way. He decides his only hope is speed. Maybe he can block the feeding machine. What Charlie can't see is that Pete's jaw has jammed, and the feeding machine rolls away empty. Pete can still win by bulldozing the balls on his side of the table. But Charlie's machine is full of surprises. We know he's got a clever projectile and a fast tractor. Now, in a nose-to-nose shoving match, Charlie shows he's also got raw strength. Thanks to this triple threat design, the pride of the championship belongs to Charlie. He'll be leading MIT's contingent to Japan, and Frontiers will be there with him for the World Series of Engineering Design.
Hello, welcome back to the studio. What you just saw there was the sophomore level Introduction to Design course. That's how we at MIT teach the design process. Now we have here with us in the studio 4 of the students who were actually participating in that design course 2 years ago. And now, of course, they're seniors. And I'm going to introduce them to you, and I'm going to ask them to tell us a little bit about what they're working on now that they're in their senior year. Charlie, tell us about yourself.
I'm a senior in mechanical engineering now, and I'm working on my senior thesis with Professor Dave Wilson. Basically, I'm designing and constructing a human-powered lawnmower, type that you ride in and pedal, as opposed to the one that you push.
Sounds like a very interesting project. Chris, tell us about what you're doing.
Well, I'm also a senior in mechanical engineering, and I'm working on finding ways to measure certain things about manufacturing systems to help optimize them.
So this is not regular mechanical engineering design. You're designing a system rather than a product.
But it's still a design problem. There's a customer and there's criterion, and it's a trial and error process to make a tool that satisfies everybody's needs. So.
Okay. Milani, what are you working on?
I'm also a senior in mechanical engineering, and I'm working on identifying key ways to improve the engineering design curriculum to make it more sensitive or usable to women and minorities.
Okay, I think that's a very important goal, because I think women and minorities have a lot to offer engineering in the United States. There are skills that women and minorities can bring in to the engineering community that we need. Susie, tell us about what you're doing.
I'm Susie Ward, and I'm also senior in mechanical engineering, and I'm also working on my senior thesis, which is to design and build a reverse-oriented pedal for a hi-hat in a drum kit.
Neat. Okay, if you have any questions you'd like to ask our panel, or David Mealy or Eleanor Baum or me, please phone in. The telephone numbers are 617-253-6753, or the fax number is 617-253-8301. We look forward to getting your questions over the next few minutes. Now, there was one question that a student in the audience was particularly concerned to ask. Brian, what was your question?
I wanted to know how long it takes to become an engineer.
How long does it take to become an engineer?
Yeah, from high school.
From high school.
Yeah.
Let's ask some of these students. Charlie, how long does it take to become an engineer?
Well, I think it depends on what you want to do. I think if you want to get out there and work, you can do it in 4 years. I mean, you can go to a 4-year school and get out and be an engineer. If you want to do more research and development type jobs, you might want to go further, go another couple of years, get your master's, go another 4 or 5 or however many years to go get your PhD. It depends on what kind of job you want.
Eleanor.
That's one of the exciting things about engineering, that after 4 years in college, you can really get a good job and do interesting work in engineering. When you talk about continuing learning, Charlie, I want to point out that that doesn't mean that you have to continue in formal education. Many engineers have to keep learning their whole lives, and there are many ways to continue that kind of learning. There are professional societies that have courses and that have meetings. There is a lot of technical literature that you can read. Your own company has courses. And the group that, in fact, is putting on this very show to you is another way of continuing your education. It need not always be in formal school. So 4 years, really, is the basic engineering education.
Okay, well, I had a question that I've been burning to ask. Susie, how did you first get interested in engineering? What was it at high school that made you want to become an engineer?
Well, ever since I was a little kid, I was kind of interested in how things worked, and I liked to use my hands, and I was interested in math and science and stuff, but it was kind of funny. It was clinched one day as I was sitting studying in my room in high school, and a friend comes frantically running into my room. Susie, you have to help me. My typewriter just broke, and I have to write this paper. And I was like, well, okay, I'll look at it. And I started playing with the springs and things, and all of a sudden, I fixed the typewriter. I said, hey, I like doing this. And so, I don't know, the hands-on stuff made me think that engineering was a way to apply my love of science and math.
So for you, it was through hands-on activity at the high school level that convinced you. Now, I think that for everybody in engineering, there was some different reason why they decided to become an engineer. We have a phone call here from Susie from Richmond. Can we hear your call?
Yes, I'm Manorama Tyler from Mathematics and Science Center, Richmond, Virginia. We have a question for Susie, because I could not understand what is a hi-hat and a drum kit is all about.
Okay, you've heard drums, or you've probably seen them play, where there's one that the drummer uses his foot like this, and the cymbals come together to go like this. And most hi-hats are played with a person's toe going like this, but I was approached by a drummer who said that he wanted to play it like this. And there are none on the market like that, and I figured if I could find one to adjust to every single one out on the market, that I could clinch a niche, that would be really interesting.
Are you going to market this product?
I have to make it first.
Okay.
Thank you.
Thank you for your question. Now, I think that everybody gets interested in engineering in a different way. Let's ask another engineer, another woman. Eleanor, how did you get interested in engineering?
Oh, my goodness. All right. At the time that I was in high school, it was very unusual for women to think in terms of a career in engineering. I was very different from you, Susie, in that I really never thought I was good with my hands. I was never someone who fixed cars. I was never someone who was an electronic hobbyist. But I was good in math and science. And I noticed that the men in my classes who were good in math and science thought about going into engineering. And I decided to do it. And for me, it was very much an act of rebellion because it was unusual. But I really want to stress that now there is an enormous number of opportunities in engineering for women. And I wanted to be very clear that you don't have to be a hobbyist. If you are, terrific, but you don't have to be. Milani, were you a hobbyist of any sort when you went into engineering?
Well, I always used to like to build model cars, and that was about the extent of my mechanical hobbies, I guess you could say. But I was always good in math and science, so that pretty much made me decide to go into engineering.
So it was math and science that was the key for you?
Yeah.
That's true for me, actually. I got into hands-on engineering after I found that I was really good at math and physics. Oh, we have another phone message coming in, and this is from, can I hit this phone call? Okay, there is another phone call coming in, but that message is still coming through. So whilst we're waiting for that phone call, let me ask David. David, how did you get interested in engineering?
Well, I think my story was a little bit more similar to Susie's. I interested in taking things apart, seeing how they worked, and trying to put them back together. I wasn't usually successful in the beginning, but got better at it. Also was bolstered by strong interest in again, math and science. I'd like to stress, though, that really the math and science are the tools that engineering uses, yet the engineering process is really how does things work and how do we make them better? If those are kinds of questions that you're asking, engineering may be the career for you.
Okay, thank you. I have one other question. Tell me about your background in high school. What was it at high school? Was there any particular teacher that encouraged you?
Absolutely. I went to high school not too far from here in Wilbraham, Massachusetts, and Dr. Brown was my sophomore honors chemistry professor, and he really gave me a strong interest in showing how science and the application of science to the real world it can be a useful and interesting experience. He also was instrumental in bringing at the time a mini computer from digital into the high school, which was new at the time and a great vehicle for learning.
Okay, thank you. I'd like to go back and ask a question of the panel here. Chris, tell me what your plans are for the future. When you graduate, what are you going to do?
Right now I'm going to graduate school at MIT.
And then?
That's the plan. And then I'm going to stay in industry for a while. Probably not in this country, but...
Tell us what more about that.
I'm in an internship program that's sending me to Japan to work in manufacturing in a plant over there.
So you're going to be working in Japan?
Right.
Which company in Japan?
I don't know yet for sure.
Do you know any Japanese?
I do.
You do? You speak Japanese? Wow.
Chris, you just said something so important, and that is that engineering is an international profession. And you're really learning skills when you become an engineer that are useful throughout the world, and more, the global nature of engineering is becoming more important to all of us.
Okay, well, let's see what's happening back here with this robot. Is it working yet?
Well, yeah, we were in the middle of setting it up, but we don't really have an experiment.
Tell us a little bit about what you're doing right now.
We're working on setting it up to do a number of tasks. One of the difficulties is we measure what the human motion is, and in order to get it to the robot motion, we have to transform that. And that's rather difficult because we have to use a lot of trigonometry, we have to measure distances and angles. And we have to be able to calibrate it so both systems move the same distance. If I move my hand 1 inch, I want the robot to move 1 inch, but the robot is built very differently than the human.
Thank you, Nate. And Nate and James are going to continue working on this project in the background. Now, we saw the MIT students in their sophomore year going through an engineering design project. But how do you get to MIT? How can you, at the high school level, learn math and science? I feel very strongly that competition, that some hands-on activity, and that the integration and testing of the science with a real problem is very important for education. Now, I think we have another phone call coming in. Let's accept that phone call. Can I hear you?
Hello?
Yeah.
This is Sam Moreno.
Sam?
Sam, yeah.
Okay, could you speak up, Sam?
Yeah, okay. My name is Sam Moreno. I'm calling from Lansing, Michigan at MSU.
Yeah?
And I want to ask Charlie a question.
Okay, go ahead. Ask Charlie the question.
Charlie, how did you do in Japan?
Actually, didn't do that well in Japan. Well, actually, we did well, but we didn't do well in the contest. My partner and I made, I thought, a good machine. We had a good strategy, but in the contest, the string from my projectile got tangled around his machine, so we lost.
Well, we're going to have a video of the contest in Japan that we can look at in about half an hour's time. So we're going to move on now, right ahead, to the high school, the Intercity High School Design Project. Let me explain what this project was all about. The students were going to build a machine, and to win in this contest they had to have a better design, had to have it well made, and had to be ready on time. This was the contest that they worked on last spring. It was called Hurricane Tech, and the goal was to develop a machine to knock down your opponent's trees. Or another way to look at that is to design a machine to protect your own trees, depending on your political bent, I guess. Now, we used this project to communicate the design process, and we were particularly concerned to get across to the students how to use engineering science in the design process, how to apply math and physics. Science can be applied in many ways. We can apply science at the feasibility stage, when we are comparing different ideas. We can apply it at the selection stage to select between different ideas. We can use science to optimize our designs. And of course, when things don't work, we use science to understand the failure. We use science a lot in failure analysis. Let's take a look at a particular aspect of the students' design project where science came in. They were building vehicles, typically. Most students built a vehicle, and they wanted their machine to be both fast and strong. Now the question is, can you build a machine to be fast and strong at the same time? Let's take a look at the physics of this problem. How do you get the maximum speed and the maximum pushing force out of a vehicle? Well, it turns out that the speed is proportional to the radius of the wheel that you use in that vehicle. So larger wheels make the vehicle faster. But it also turns out, from applying the physics, that the pushing force is inversely proportional to the diameter of the wheel, to the radius of the wheel. So a larger wheel makes the vehicle less strong. If you want to have a strong vehicle, you need smaller wheels. And this is a typical engineering design problem. There are two goals that you want to optimize. You want to make a machine that's both fast and strong, and somewhere in there is the ideal wheel radius. And in order to win this contest, the students had to find that appropriate wheel radius. In a few minutes, we're going to cut to that video, but right now we have another phone call coming in. Let's hear this phone call. Yes? Okay, a little bit of hum there. Okay. Let's show the video, and then we'll come back to that phone call. Okay. Oh, is the robot moving? No. We're going to show the video. This was the kid. Cardboard tubes, pieces of steel, bits of string, strange plastic parts. It might look like just a box of junk to you, but to the students at Cambridge Ringington and Latin High School, this is the raw material for the machines they're going to build. They don't have many tools, but they've got great ideas and they want to win. You see, they're going to be competing with these machines. Each team of students is building a machine to knock over the opponent's trees. Other teams are trying to protect their own trees.
Ready and go.
This one works. But in the end, it was one of the simplest designs that won. Meanwhile, across the Charles River at Boston Latin High School, science students there have been doing the same design project, and now they're coming to take on the Cambridge students in the first intercity design contest hosted by MIT. The audience of students and teachers and parents, they all seem to be having a good time. Each team has just 30 seconds to set up their machine. It can be hard losing. Especially when your machine falls apart. or you can't steer. But really, all the students were winners because they all managed to build a working machine. The first Intercity Design Contest champions, Jose, Millery, and James. Welcome back to the studio. That was the first Intercity Design Contest championship, and that was held last May between the cities of Boston and Cambridge. We ran another contest. The students and teachers of Boston and Cambridge organized another contest last December, and there was a winner there. I'm going to explain what the contest is all about, and then the winner is going to show how they won. And then we're going to do a rerun live in the studio of the final contests between Boston and Cambridge. Okay, the winners last December were Ben, Stanley, and Rob. These are science students at Boston Latin High School. Congratulations, guys. And this was the machine that they built. And with this machine, they won. What was the goal? The goal was to build a machine out of a bunch of scrap parts to knock this ball into the opponent's half of the playing field. At the same time, of course, their opponent was trying to do the same to them. In doing this, they had to learn some science. They had to learn how to use electric motors. They had to learn some fabrication skills, not manufacturing, but fabrication skills, because they had to build that machine. And they had to learn to work as a team. They built this machine as a team. And I think you had a good time, right? Okay, let's see how your machine works. Irene? You can see why they won. Okay, now we're going to run a new final between the city of Boston and the city of Cambridge. And can we have the first contestants, please? Can we have the two Cambridge machines in the semi-final? Okay, Wesner. Wesner won the local contest that was held at Cambridge Ringe and Latin High School last December. But then in the Intercity contest, you didn't do quite as well. What happened in the Intercity design contest? Plug came loose. Yeah, there's always something. Paul, you came in second in the Intercity, in the Cambridge contest, I believe, last December. What do you think is going to happen today? Okay. You ready?
You guys ready? Ready, set, go.
Well.
Green is the winner.
Well, I think that was quite clear. Paul's machine won. And you have a teammate, right? Robert, who's around there someplace? Okay, Paul's machine won. Why do you think you won?
Well, I had more weight on the back of the wheels than he did, so I had more traction.
Okay, there's some physics involved there. He had more weight, he had more traction. In fact, they have about the same size wheels, but because of the increased weight in Paul's machine, he got greater traction, which pushed Wesner's machine off. I'm sorry about that. Okay, let's look at the two machines from Boston that are going to compete in the semi-final. Let's get those machines on the table. And Paul, you're going to hang on to your machine, right? Okay, whilst these machines are setting up, we have another phone message that's come in, a phone question that's come in. Can I hear that question?
Hello?
Yeah?
Hi, I'm from Dexter, Michigan,
Mm-hmm.
in Wiley Middle School, and I have a question for Susie.
Susie Ward.
Yeah.
Okay, let's find Susie. Come over here, Susie. What's your question?
Okay, and earlier you mentioned mechanical engineering. I was wondering how many types of engineering there are, and what are some of the other fields that are available to us?
Well, let's see. At MIT, there's a lot of different fields. There's civil engineering, ocean engineering, chemical engineering, mechanical engineering, aeroastro engineering. It goes on and on. But I think you know, it depends on you and it depends on where you go in the field. I mean, you can do stuff with computers. You're basically unlimited.
Okay, thanks a lot.
Thank you for your question.
Yep.
Okay, are we all set here? Irene?
Okay, ready, set, go. Okay, looks like red is the winner.
Okay, this time round it was red that was the winner. So we have a winner in the semi-final from Cambridge and a winner in the semi-final from Boston. Now let's see who's going to win when Cambridge comes up against Boston. Paul, is your machine going to go on the table? Great. Let me introduce you to these people. This is Jose Rodriguez, and you won in that first intercity contest last May. And now it looks like you're coming back to win again. What do you think is the secret of your success?
It's pretty much the teamwork that we all had good ideas that we all were able to put into the car. It just wasn't like one person. I don't know.
Okay. Mallory, tell us about some of the good ideas in your machine.
Well, this machine, our first objective was we knew that a lot of people were going to build projectiles, so we just wanted something to block it. And just good driving, makes a good team.
Okay. Are we ready?
Okay, ready, set, go.
Oh!
Looks like we have a winner, green.
Yeah! Okay, can the winning team come round here? And I'd like to introduce to you now Mr. Ken Reeves, who's the mayor of Cambridge. Ken, could you come round here? Sure.
Well, I'd like to say it's a great pleasure to be here first and to say hello to the audience from Cambridge and from Boston, and to say we have a number of awards, but the very real first place award in the Discover Engineering Inner City Design Contest 1992 goes to Paul and Robert from Boston Latin.
Cambridge.
Sorry, I'm sorry. From Cambridge. So it's with a double amount of pride. See, with Cambridge people don't come stamped, but I should have known. Listen, congratulations. We're very proud of you for winning on behalf of the city, and it does seem that everybody has put together quite marvelous machines with projectiles to win. So congratulations and thank you.
Thanks.
Job well done.
Okay, thank you, Ken. Now, if you have, congratulations to Cambridge. You lost the first time, lost the second time, but the third time, Cambridge is a winner. I'm really glad because, you see, I work in Cambridge, MIT's in Cambridge, and a couple of high school teachers over there are going to kill me if Cambridge didn't win this time. We have a phone question coming in. Do we have that phone? No, apparently we don't have a question coming in. Okay, we have another panel that is setting up over here, and if you do have questions, please call in. The telephone number is 617-253-6753, or the fax number is 617-253-8301. And I'm available to answer questions, Eleanor Baum and David Mealy. And also we have a team of teachers and science coordinators for the City of Boston and the City of Cambridge. Let me introduce them to you. Okay, can you say a few words about yourself? This is Chris Newton from Cambridge Ringen Latin High School.
I am a teacher, a physics teacher at Cambridge Ringen Latin, and I graduated from MIT last year and worked on this design, this way of teaching design in high schools as my senior thesis project last year.
Steve from Boston Latin.
Yeah, I'm a science teacher at Boston Latin School, and this is the second year that we've done the intercity design competition, and we're hoping to expand it statewide, nationwide, and who knows how.
Melanie Barron, coordinator of science at for the City of Cambridge.
We were delighted to be one of the first high schools in the nation to be contacted to work with MIT and to participate with Boston Latin School in this contest. One of the reasons it was so exciting is because this contest has all of the elements of what's important about good science education. It involves students, it has no blocks to their participation, it's interdisciplinary, it's exciting, it poses a real problem that really has to be solved by doing something about it, involves teachers, involves parents, involves the community, and it also involves public schools with a genuine partnership with an institution that's a partnership of equals based both on trust and mutual need, and worked out very nicely because of that.
Thank you, Melanie. And Ann Hamada from City of Boston.
I'm the program director at K through 12, and I'm very happy, obviously, to be here also today. And I'm also very excited by this design competition because, in addition to what Melanie has said, I really feel that this is another way, another avenue to stimulate science interest, in addition to the traditional avenues such as science fair and classroom lab activities. So I think that's very important. Another benefit that I see is that this type of activity really features teamwork, and I think that's more reflective of the workplace today. And I think it also focuses on technology, which is distinct from science, and I think that's something that needs to be told to both the school student and also to the general public. So I think it serves a great need both for the children and for society.
Thank you very much. I think that Eleanor Baum had a question that she wanted to ask. No? Millery had a question. Congratulations, Millery's part of the winning team. Good job there. You had a question.
Yes, I'd like to know what kind of schools can students go to study engineering?
That's a terrific question. There are about 300 schools in the country that have accredited engineering programs. And you can find a school that's right for you. There are big schools, there are small schools, like my Cooper Union is one of the small schools. There are private institutions, there are public institutions, state universities. There are places probably close to your home, and you have an opportunity to go to other places in the country. So there's really a large number of programs to select from if you decide to become an engineer.
Thank you. If you would like to phone in, ask any questions of our panel, please call this number, 617-253-6753. Now I have a question. Steve, tell me about the impact of this type of project on the attitude of your students towards science.
I think this type of project is a project which really motivates the students when they could get their hands on to the activities as opposed to just reading about science or studying it in a book. I think they learn a lot more when they participate in the process. I also had a question myself for some of the students, and I'm sorry that the MIT student panel has already left, but my question was for either Susie or Melanie. They talked about what motivated them to go into engineering, and I was interested to see if there was anything that they could point out as a stumbling block.
Melanie, come out here. Okay, your question is, what are the stumbling blocks that our students perceived between them and a career in engineering?
Yeah, especially for Melanie, since she's working in this curriculum, changing the curriculum to increase enrollment of women in engineering.
Okay, Melanie, tell us about that. What do you think?
Well, for one, you have to have a very strong heart to get through engineering, to get through MIT, and I'm very confident. So that's one key thing, is the confidence. And I'm very interested also to find out how I can develop and find ways of developing the curriculum, to make it better, to make it more interesting for everyone. That's what my main interest is. So.
Okay. Do you have some comments, Eleanor?
Yeah, I think what you're doing is absolutely terrific, Melanie. And did you find that being a woman was a difficult thing in your study of engineering and classes and such?
Actually, coming to MIT, I thought it would be predominantly male, but you come here and I don't really find a lack of women. I mean, I'm really comfortable. I don't feel at all ill at ease while I'm here. I feel very comfortable here. It's not a problem.
That's terrific, and I think more and more that's becoming the case, so that women who do go into engineering really don't feel strange or uncomfortable, but feel very welcomed and very part of what's happening. I wanted to just make one other quick comment for our viewers throughout the country, and that comment concerns JETS. There is a national organization which deals with high school students who might perhaps be interested in engineering or technology, and the name of that organization is JETS. JETS has groups in every state and all over the country, and I think JETS in some states also has this kind of contests. So that may very well be something that students look into in their own area.
Okay, do we have any telephone questions? We have a question from the audience. Sir, please come out.
I have a question for Chris Newton. You said you graduated from MIT just last year, and now you're a teacher in a high school. I may not keep up with what's required, but it used to be that you had to take education courses at a teacher's college to get accreditation.
Yeah.
And I'm wondering what your situation is.
Okay, I decided during my junior year at MIT that I wanted to be a teacher, and I did all of the education requirements and certification at Wellesley. There's an exchange between Wellesley and MIT.
Hello?
And so I've gotten my teacher certification in physics and math through Wellesley.
So you both qualified as a teacher and as an engineer,
Yeah.
and you decided to go into teaching.
Yeah.
That's great. I mean, you're aware, I suppose, that you're accepting half the salary you could get if you stayed in engineering.
But that you're doing very important work. Bravo.
Okay. Melanie, could you tell us a little bit about what you think is going to be the future of science education in the city of Cambridge?
We are beginning to embark on a revision of our elementary curriculum and starting working with you and working with this kind of effort to also look at the high school curriculum, moving toward much more of an integrated, interdisciplinary, hands-on approach to science education. It's going to take a lot of work, a lot of partnerships, and we're looking forward to about 5 years of long, hard, exciting work, hoping to move toward a very changed but reflective of what's needed now in the future curriculum for the city of Cambridge.
Okay. Do we have any questions? Yes, I think we have a telephone question. People seem to have difficulty getting through because if you phone when somebody's talking, we're going to keep you on hold until the person who's talking, Melanie, in that case, until Melanie finished talking. Okay, has the telephone line come back on? Could you ask a question, sir? Hello?
Yeah, I'm interested in agriculture, and I know there's agriculture and engineering, but what jobs are contained in agricultural engineering?
Well, I'm not qualified to answer that question because we don't teach agricultural engineering at MIT. Agricultural engineering is a very important subject. I know that because that's what's enabled America to become essentially the breadbasket for the world. We export so much food to feed the rest of the world. Eleanor, could you speak on that subject?
I know there is an enormous need throughout the world for agricultural engineers, and there are many accredited programs in agricultural engineering. Very often state universities have such programs, and I would check with the state university in your own state.
Okay. We have another telephone message, another telephone question. Please go ahead. Hello? Hello? Please go ahead. Hello? Okay, that didn't come through. Anne, tell us about your plans for science education in the city of Boston.
Generally, I think I can articulate 2 overall goals in that I want our graduates to be science literate citizens. I want them to be part of the science competent workforce, I believe, of the next century. And I see that basically, I see achieving those goals basically by emphasizing positive attitudes in science. So I see it starting in the elementary grades, where using manipulatives to give hands-on and cooperative type activities to teach science and to teach content is one end, but the other is to produce some positive atmosphere in the classroom and positive attitudes. I see mostly in the middle school a time of really increasing aspirations in science. Okay, and I think that probably the best way to do that is through having what now is called thematic modules or units. And then I see really increasing the program in the secondary schools, that it has to be more extensive than just 1 or 2 required courses, as is currently the case. And I think that that has to be both a combination of enrichment classes and advanced classes. And I think that if you do that, then we can achieve, and I plan to achieve those 2 goals, as you say, the literacy in terms of citizens and the competency in terms of the workforce.
Yeah, thank you. Eleanor, how do you feel about that?
Anne and I had a very interesting discussion about this very topic before showtime. We talked about the fact that we live now in a technological society, and in order to be a citizen in the society, in order to be able to make intelligent decisions when you vote, really involves an ability to at least read and understand a little bit about some of the technology that's involved. And I think what you're doing, Anne, is very important with understanding the difference between science and technology and worrying about technological literacy for people who aren't necessarily going to be scientists or engineers. It's something all citizens need, and I thank you for those efforts.
Steve, how do you feel about the importance of technological literacy, particularly amongst the minority community?
Well, I feel that we have to, we're living in a society which is highly technological, and to some extent it makes people feel somewhat alienated from the world around them. To deal with these machines, microwaves, televisions, cars, you know, you name it. And people don't know how they work. And it's getting to the point when people feel like they're living in a world, but they don't really know what's going on around them because they don't have a good grasp of the technology. And I think that just so that people feel more comfortable with the world around them, they should know more about physics, science, technology in general, and in particular for people of color. I think that if we're ever able to get out of the rut that we're in, people are going to have to learn about technology. I think that's really the way out.
So you think that understanding technology, understanding science and math is going to helps you to be a more powerful citizen and helps you to earn more rights in our society?
Right, I think that technology is the key to people getting control and independence of their lives.
That's a pretty powerful statement, Steve. Thanks.
Okay.
I agree.
Dave.
Go ahead. I agree very much. I'll tell you, though, that I got a VCR that I'm still not sure I know how to program all the way. But I have a question for the panel, though. I think in conjunction with math and science, I think there's other parts of the education system that are very important to engineering. Certainly communication through the English programs, as well as the teamwork that you may learn in athletics or external activities. Given that teamwork and application, as you mentioned, Steve, are valuable aids to learning, what specifically might we hope to see in the future in the education programs for anybody?
Melanie.
Cambridge is spending a great deal of time and money and commitment on staff development, looking at exactly what you're talking about in terms of working with teachers about cooperative learning, encouraging students to work in groups, increasing the amount of time and equipment in classrooms so that students do the work rather than are lectured to. At the elementary level, and like Anne says, the phrases at this point are PAT, interdisciplinary, thematic types of units at the elementary level. In Cambridge, we are getting to be very serious about integrating with not just mathematics, but with English, with the literacy centers that we have, and looking at using science as a tool in the way that engineering uses math and science as a tool to help elementary students learn the skills of reading, writing, thinking, which science gives you a reason to want to be able to read, write, think, and ask and answer questions. And in that way, I hope we will have an exciting elementary science program that begins to move toward what you're talking about.
Melanie, I'm sorry, Harry, we're both eager to do this. The kinds of skills that you're talking about is something that engineers have to be very, very concerned about. You can come out with the greatest device in the world, but if you're not able to present to people what you've done, it's pointless. So you have to learn to speak well, you have to learn to write well, and in many kinds of projects, you even have to learn advocacy. That's one of the great areas where I think engineers have failed. Engineers have really given up technological leadership to non-engineers, to politicians. And very, very few engineers do things like go into politics. And that's something that I really would like to encourage. The end product of engineering doesn't have to be working for an engineering company making devices. You can use engineering as a background to a whole lot of other pursuits.
Okay. Thank you, Eleanor. In fact, we just have a question coming in from Mary Armitage, Saginaw Valley Community College. And Mary has a question for Eleanor Baum again on the subject of women and minorities education. Eleanor, what is the most significant thing coming out of your research? And what is a significant aid in your study of women and minorities?
The most significant thing, I think, that's coming out is that those women and those minorities who've decided to study engineering, who've decided to become engineers, are very satisfied with their career choice. And I am delighted that they seem to be going into engineering for all of the right reasons. They like the challenge of solving problems, they want to do interesting work, they want to continue to learn and grow, and they want to help society. So I think for all people, not just women and minorities, engineering really provides a satisfying avenue for fulfillment in a career.
Okay, thank you. We are now going to cut to a tape of the International Design Contest that somebody asked about a few minutes ago. Before we cut to that tape, we're just going to take a quick last look at James and Nate's robot. And Nate, somebody phoned in and they wanted to know, how does this robot know where this object is?
That's a very good question. In fact, that's the key of the programming. This robot doesn't have a vision system, which the human usually uses their eyes to figure out where this is. So indeed, we have to tell the robot where the starting position is. The point is, right now James is going to teach the robot how to sweep and clean up. The robot really doesn't know where the mess is right here. It doesn't know where the table is. It just knows one spot. All the motion that is going on, James has to teach it. If the robot, in this case, in fact, the robot has sort of a disadvantage, because if this cup moved, the robot won't be able to figure out what it is. And some of our work is to improve the robot. So either one could use a vision system, or one could add to the robot touch capability. I wanted to just point out a few things that involve the type of work that we're doing. One of them, in the area of robotics, it's very exciting, because we get to use a lot of the latest technologies. We get to work in mechanical engineering, we get to work with electrical engineering, we work to combine the two using computers, and we get to work with some of the latest type of sensors. James, maybe you could tell us some of the work that was involved in developing these tongs and other work that you've did.
Part of what's gratifying to me as a mechanical engineer is I get an opportunity to use electrical engineering skills, electronics, mechanical engineering, computer programming. We have to integrate it all into a product that works and uses all these different facets in an intelligent manner. So that's very exciting, and it points out the fact that if you are a particular type of engineer, you're not limited to exactly what you're doing, you know, with mechanics or whatever.
Let's see what the robot can do now, if it can go. If it can figure out. Let's see if the robot can sweep off the little items here. It's working slowly but surely. Looks like maybe we've accomplished this. It's reaching out in rotations. Rotations were some of the hardest things to program the robot. Is it going to get the last one? I don't know. Lo and behold, it did. Well, great.
Okay. Thanks, Nate. And I just got one question here from John Marshall High School, from Brian of John Marshall High School in Milwaukee, Wisconsin. And he asks, are you going to incorporate voice command in the robot to make it more user-friendly? And the answer is yes, we just didn't get it ready in time for the show today. But if we do this again next year, we'll have voice command. Now, we just saw a couple of engineers working as a team on a design engineering problem. Engineers always work in teams. You know, you can go to one lawyer and he can sue somebody. Go to one doctor, he can give you a piece of advice. Engineers have to work together because the problems we work on are so complex. Today, engineering is becoming very much more international. Today, the products we buy are often produced by engineers working in many different countries, particularly in Japan. We all know how many products we buy have been designed by Japanese engineers. But often they're designed by Japanese engineers working with American engineers. Take the Ford Escort or the Mazda 323, for example. That was designed by American and Japanese engineers working together. But it's very difficult because in American and Japanese, we speak different languages, we have different cultures and different backgrounds. We're very interested in this problem, and to understand it better, we asked some of our MIT students to go to Japan and to collaborate in a joint design project in Tokyo. Let's take a look at that tape and see how those students did in Tokyo.
When the world's craziest contest goes international, can Japanese and American students play on the same team?
GTE brings you more than the power of telecommunications, light, and precision materials. A grant from GTE also brings you the power of a new world in scientific American frontiers. At GTE, the power is on.
Hi, I'm Woody Flowers, host of Scientific American Frontiers. This is one of the current generation of sport utility vehicles. I think they're marvelous. As you can see, they're powerful, tough. They're also quite comfortable and reasonably economical to operate. Really good engineering. This one's called Navajo. Must be designed for the American wilderness, right? Well, look at the name tag. It's Japanese. Have they done it again? Beaten us at our own game? Well, not exactly. Sometimes things are not the way they seem. I'm getting ahead of myself. We'll get back to this in a little while.
For years, a popular course at the Massachusetts Institute of Technology has asked students to build their own game-playing machines from a kit of parts. This year, for the first time, the MIT idea has been exported to the Tokyo Institute of Technology. Japanese students received an identical kit and the same engineering challenge. At both universities, the students had just 6 weeks to build their creations. Then at MIT, there was a tournament to see who could pull the tennis balls down from a mountain and deposit the largest number in a trough on the game table. The excitement's contagious. And when the Tokyo Tech students staged their contest, it was clear that this cross-cultural transplant worked. But there's more to come. The top 10 from Tokyo Tech will meet the top 10 from MIT in a World Series of Engineering Design in Tokyo. The American students take with them the machines they built and the engineering savvy they've gained. But that doesn't feel like much as they set out for the engineering capital of the world. In Tokyo, they're welcomed like celebrities. After all, the Japanese students think MIT is the engineering capital of the world. Each team has just 6 days to design their machines, and on this modified table, the contest will be tougher. The tennis balls start out on a higher mountain, and they have to wind up in a raised area the same color as each starting square. But all that's just engineering. The real challenge is communication, because teams will consist of one American student and one Japanese. Suzy draws Toshihiro's name. They can shake hands, but can they talk? For Irene and Daiki, just learning each other's names is a hint that communicating is not going to be easy.
Irene-chan.
Irene-chan. Daiki Kamiya.
Daiki Kamiya.
Yes.
How can the teams design machines together when they have barely a few words in common? The joint contest organizer, MIT professor Harry West, has a suggestion.
Therefore, we would encourage you to make full use of the pens and papers and other material that you have for communicating. So try to communicate graphically.
Another thing is this.
It looks like this scheme can work. Chris and Naoto are doing plenty of scribbling and nodding. But when Susie tries to get across her strategy, it seems there's no communication at all. Toshihiro just doesn't get it. And the awkwardness continues at the party that night. Like all college kids, they know how to eat and drink. But the American students are flustered when the evening takes a more Japanese turn.
What are we doing here?
Until the traditional welcome dance begins. And then something does start to happen. The American boys, with Greg and Chris in the lead, take the first clumsy steps to join the Japanese dancing circle. Maybe rock and roll would have worked too, but in any case, the barriers between the two groups begin to come down. While nobody had known quite what to expect, the first day ends on an encouraging note. And the new camaraderie carries over to the next morning. Irene and Daiki are working together in earnest on a joint strategy.
スタートしたら大きいマシンがそこまで行く。で、それから小さいのを出して山を崩してからボールを集めます。
In the original contests, the students all set their sights on winning. Now they're recognizing that the goal of this international match is different.
Whoever wins, I don't think that's really the point. I think just the fact that if you can produce something by working with someone and having no language in common is a great accomplishment.
But some of the American students are puzzled about how to work together. Chris, for instance, is confused because Naoto seems so unassertive.
I think the Japanese students seem to want to really blend and really try to cooperate more rather than taking a strong leadership role.
In Japan, students learn to cooperate. It's one of the factors behind Japan's economic success, and it's especially important in engineering.
Design is in many ways the process of negotiation, and clearly the Japanese students are very good at doing that because they have this natural sense of trying to get together and form a consensus. For the American students, at least to begin with, it's a little bit more of a challenge.
Time away from the shop obviously helps, and the bright lights of Tokyo by night have a lot to offer. But it turns out that Chris and Naoto have exactly the same idea of a good time. Will they be able to bring this more comfortable companionship back into the engineering shop? Already, the few days allotted for constructing the machines are almost over, and something new is happening. The students have discovered they have a common language after all, the language of engineering. We don't have a clue what Toshihiro's actually saying, but it's perfectly clear to his fellow engineer.
It's a universal language because the strength of steel is the same here as it is in the United States. The fundamental physics, which describes the behavior of an electric motor, is the same here as it is in the United States. So the students have this very large background that is common, all the physics and engineering and mathematics that they've learnt. That makes it a truly international subject.
A scramble to test their creations and fine-tune their strategies. And suddenly, it's the last day before the contest. To showcase the different machines, Harry West schedules a warm-up event. Each team gets to play a demonstration round without any opponents. Daiki's big transporter neatly delivers Irene's harvester right to the top of the mountain. Remember, what counts is getting balls into the raised trough. This may be the most brilliant design of the lot. A tank with incredibly flexible joints. It can sweep off almost all the tennis balls and then bulldoze a lot of them at once up into the trough. Decked out in matching headbands, Chris and Naoto have put together a true joint strategy. While Chris's huge contraption lumbers into position, Naoto scales the side of the mountain. This is real teamwork, and although it takes Chris a long time to maneuver his big machine to the other side of the table, the payoff is worth the wait.
5 seconds to go. I think the teams that have been most successful have been those where the two members have been on the same bench all the time. They've gone out together, and there's been the sense of a common understanding as to what needs to be done.
A former Tokyo Olympic Stadium, the imposing site of the joint contest main event, and inside, an extravaganza that will be broadcast by Japanese TV. The elaborate display shows just how highly engineering is esteemed in Japan. With all the pomp that Americans normally reserve for sports heroes, each team is formally presented to the audience, in the hall and at home. And although they're only teenagers, these young engineers rise to the occasion with poise and dignity.
5, 4, 3, 2, 1, start!
For Chris and Naoto, the first match starts just the way they planned it. But then Chris's machine is shoved away from the center of the mountain, revealing a conspicuous design flaw. Now he's not perfectly lined up, so the balls aren't making it into the trough. Their opponents, the green team, are winning, 4 balls to 2. Time is running out, and Chris is jammed. But Naoto has a brainstorm, drives up the other side of the small mountain, and pushes green's balls into the red trough. Victory at the last minute with an improvised strategy. It looks like it's going to be a great contest. But when Irene and Daiki come up, things don't go so well. They never get a chance to execute their strategy. Their opponents have one machine just for defense, and it bulldozes Irene's harvester into a corner. That's enough to take Daiki and Irene out of the contest. And it turns out this obstruction strategy knocks out team after team, including Chris and Naoto, and Susie and Toshihiro. All too soon, it's time for the finals. The flexible tank makes the first move. But this smaller machine is quicker where it counts. And then, again, the match turns into a defensive battle. The flexible machine is pinned. And since Red has balls in already, that's all it takes to win. But winning the tournament is not what this week has been about. It's been about getting along in spite of barriers, about taking pride, nerd pride as the button says, in learning to work together as engineering partners.
We are the king nerds of this contest.
And about discovering many new ways to communicate and cooperate. As the future top engineers of the United States and Japan, these students have been building some of the most important bridges they'll ever work on. And that, says Harry West, is the point.
It's very important for American engineers to learn to cooperate and to be able to work together with Japanese engineers, because a lot of them are going to be doing that in the future as part of their job. we're going to have to learn to cooperate with other countries as well, Britain, Germany, and France. The future is international, and we either recognize that or the rest of the world will just pass us by.
I think Harry West is absolutely right. The future is international, and it's already here. Take a closer look at this apparently Japanese vehicle. Although it has a Mazda nameplate and a few parts made in Japan, the engine was built in Germany, the transmission is from France, the wheels are from New Zealand, and it was designed by Ford and assembled in their plant in Kentucky. The auto industry is global nowadays, and a lot of other industries are heading that way. The kind of partnerships that we just saw formed by the students in Tokyo are already a necessity.
Hi. I'll tell you, from watching that tape, the computer industry also is global. The component I showed you in the beginning of the program is part of a mainframe in the IBM mainframe family, and that's made in Yasu, Japan, Montpellier, France. We have components from Canada, South America, and all over the world. It really is important to manage global engineering. We have teamwork, which we regularly work with engineers in these other countries. We communicate regularly over the telephone, satellite links, and electronically. So really, I think it's very important that we learn to communicate with all the folks of the world. Another message I'd like to leave you folks with who are considering careers in engineering and science, if you ask yourself questions like, how does it work? Why does it work? How can I make it better? You like to take things apart, hopefully like to try to put them back together. I really think you ought to look further into a career in engineering. Remember that science and math are tools, so is teamwork, so is the communication. With that, I'd like to wish you all good luck and enjoyed being with you. Thank you.
Eleanor.
I hope we leave you with answers to why engineering, or at least some answers. And some of those answers are because it's interesting, it can be fun, and it leads to a lifetime of interesting work. But you can't make a decision to be an engineer at the last moment. What you have to do is when you're in high school, remember, you've got to get that math and science preparation, because without that preparation, you won't be able to have the opportunity to become an engineer.
Thank you, Eleanor. Now, first of all, I'd like to apologize for all the listeners who've been phoning in. We've just been inundated with phone calls over the last few minutes with people with burning questions. And I think we have just a few minutes left, so I'm going to try to get a couple of questions in. We have a question here from Mindy Wilson, Virginia Beach, Virginia. General question, which we're going to put out to the panel. We have a new member of the panel, Irene Chow, I'd like to introduce. Irene, pleased to have you with us. Irene, do you have to know you want to be an engineer before you enter college?
I don't think you need to know for sure that you want to be an engineer, or for that matter, specifically which kind of engineering you want to go into. At many universities, including MIT, you come and you take core classes which introduce you to science and engineering. And then once you've taken these core classes, then you have a better idea of where your interests lie. And then once you've taken these classes, you can better decide specifically what field you want to go into, whether it's engineering, science, or which specific engineering field you want to go into.
Thanks, Irene. And I'm going to get through a few more questions here. A question for Chris. This is from April Johnson of Gadsden, Alabama. And again, a general question. Chris, if I were to go into engineering, April asks, how would I be sure that I would get a job?
That's a good question. I'm not really sure how to approach that. I think that if you work very hard during your studies and are persistent and are truly enjoying what you're doing, I think that'll all come out in the end, and you'll be able to find a place. maybe difficult depending on the times, but if you keep at it, I think that you won't have much of a problem being successful.
Yeah, just speaking for myself, I did graduate in engineering. I decided eventually to go into teaching engineering, but engineers are typically inundated with jobs, and we have some professional engineers out there in the audience, and if we get a camera on some of them, maybe they can give us some advice about the demand for engineers in our community. Engineering profession is in great demand right now. We have another question here from Evans Fitzgerald, Dexter, Michigan. Engineers are problem solvers. What are engineers doing to solve the ozone problem? Well, I'm going to answer that question directly because I have been working with some companies working in air conditioning. Air conditioning uses chlorofluorocarbons. That's one of the chemicals that makes an air conditioner work, or refrigerators work. And it's also those same chemicals that lead to the ozone problem, the decreasing the level of ozone in the atmosphere. Those engineers are working to develop new chemicals which don't deplete the ozone layer. They're working to develop better insulation for housing so that we don't need as much air conditioning. Engineers are working to solve this problem. Now, we really have run out of time for any more questions. So at this stage, all I can say is if you have a question, call my answering machine, 617-253-2018. I'll personally answer your question after we get off the air. I'm really sorry we ran out. We've just been inundated with questions. And at this stage, I'd just like to thank everybody for participating in this project. I'd like to thank the audience throughout the country who've been watching this on the NTU network. Especially we'd like to thank the people who've made this possible. NTU, the National Technological University, MIT, of course, and also Hewlett-Packard and Motorola, because those are the people, that's the company that put up the funding to make this project possible. I would just like to thank you for doing that. Also, I'd like to thank the students of Boston and Cambridge for participating in this project. And Polaroid, which is a Cambridge company, has phoned in to say that they have a prize for all the participants in the final of the contest. And let me introduce a couple more people here. The mayor, Ken Reeves, Mary Lou McGrath, who's superintendent of Cambridge Schools, and Ed Saracen, principal of Cambridge Ringe and Latin School. They're going to be giving out the prizes to the students. So can we have the finalists coming forward to get their prizes? Once again, thank you very much for participating in this show. We hope you enjoyed it. If you have any more questions, phone my answering machine. I'll get back to you, 617-253-2018. Also give a few more credits. I'm just going to read some out. I'd like to thank GTE, who funds the program, and it was excerpts from that program that we were watching on the MIT Design Contest. I'd like to thank IBM, in particular Jack Keeler, Honorary Chairman of National Engineering Week, and Polaroid. Thank you very much.